So we are asked to use the graph shown in the figure below. All have the form, okay. So we have f of x equals f of x, oh, I'm sorry, a b to the x power. So this is our function. A constant in front, which is a, times the base raised to power x.
Are we still in 6.3?
This is from 6.2. This is 6.2, problem 4. And we have, thank you for bringing the graphs, otherwise we would have not been able to. So which graph has the largest value of b? So if you remember, we said this. The higher the power, if it's greater than 1. The higher the power, the closer the function gets to the y-axis. If the base is 1.1, it could probably look like this. If the base is 2, it would probably look like this. If the base is 3, it will look like this. If the base is 10, it will look like this. So now they're giving us few options here. Now, they're not telling us which, it only says which graph has the largest value of b. So first of all, they're not telling us, we have to look at both situations in which the base is 1/2 and the power could be negative. So it could happen. So let's analyze each graph. So this one is definitely a base greater than 1. This one is definitely a base greater than 1. This one is definitely a base greater than 1. This one, if there is no transformations, okay, so if there is no transformation, because if there is a transformation in x, but I have to assume that there is none, because it's not negative x, right? So this has a base less than 1, because it's decreasing on all its domain.
But it's not negative, being that is.
The base cannot be negative. The base can be between 0 and 1 and 1 and infinity. This one is definitely base less than 1. And this one is definitely base less than 1. So in this first question, otherwise there is another, which graph has the largest value for b? I will definitely choose the one that is closer to the y-axis. Is that clear? Is that clear? One more time. So this has base 1.1. This has base 2. This has base 3. This has base e to the x. This has base 10. And then the further away I go from the y-axis, the smaller the base becomes. All these ones, because x is positive, has positive in front, I meant to say, all these ones have a base less than 1. So I would disregard them, because it says which graph has the largest value of b. Is that okay? So now I see here another question, the largest value for a. Is that the second question of the same problem? Okay, so again the same thing, because if this, see, they're all, if you remember what we did with x squared. So this is x squared, twice x squared, 3 times x squared, again x squared, 1/2 x squared, 1/4 x squared. So it still has to be the same thing. Any questions? Very good question, thank you. As I mentioned, I always encourage you to bring questions to class, because there is no way I can cover every type of function question, type of equation, problem, word problem in class. There is no way. Okay. Okay, going back to chapter 6, is there anything else you have for me? Anything else? So let's go back to, we stopped here. We stopped here on page 497. I can go back and look. We looked at solving some log equation. I can go back and exactly tell you which one was the last problem. We looked at was 31. 31 on page 497. Yes. So we looked at 31. This was the one that we stopped at. Okay. I think we should look at another exponential. I think we should look at another changing these into log form, and simplify something from here, and so on and so forth. Ready? Do I get to choose? Or you, yes? Which one? 23 it is. So here it is. 23 and 23, we have y to x equals 39 over 100. Y to x, 39 over 100, and this is problem 23, page 497. In this problem, we are only asked to rewrite this equation in logarithmic form. So let's write the equation in logarithmic form. So here's how I would address this problem. I would write the most important relationship, which is log base a of x is y is equivalent to a raised to y equals x. A raised to y equals x. This is what I know. And by similarity, I will put this on the right-hand side as y to the x equals 39 over 100. And all I have to do is identify what goes as the base, what goes as x, and what goes as y. Not difficult. So let's look on the right-hand side because I have to start with the base and I have to have the base. Can anyone tell us what is the base on the right-hand side? Y. What do we raise the base to? X. To get which number? Done. We don't have to do anything else. So the base raised to x equals 39 over 100. So please don't get scared about these. They initially look kind of weird. Always write the conversion between log equations and exponential equations, and you can come up with anything you want. Whatever they ask, you'll be able to write it. Do we need another? Please choose if you think we need another. Okay, I'm going to look at 22. I would like us to be a little bit prompt more because we have so much to go through. 7/5 raised to the mth power equals n. The same question here. We are asked, the more you write it, the better you remember it. Log base a of x is y is equivalent to a raised to y equals x. And put on the correct side what you are given. I'm given 7/5 to the mth power equals n. And all I have to do is identify the base, identify what I raise it to, and I identify the number that I apply log to. So, what would you say? So the base is 7/5, very good. 7/5 is raised to m, and the number is n. Very good. Perfect. Let's look at 35. Any questions? Stop me, please. We are never in a hurry when there is a question.
So always stop me, please. Okay, let's look at 35. Natural log x equals 2. They want us to come up with the exponential equation. Remember we said ln doesn't have a base. Well, it has to have a base. What is it? E. That's the only one, actually two, that we do not write. So e raised to which power? 2 equals x. Perfect. Now, I'd like to simplify.
38.
Yes, you said 38?
Yeah.
I was just looking at 38. Thank you for choosing that. So 2 log 0.0001. Again, I don't see the base. What is the base? 10. The base is 10. Very good. Leave the 2 alone for now. I'm going to come back. So let's just determine log of, or common log of this. I don't know what it is, but I know it's equivalent to base raised to whatever number. I get 0.0001. Since I raised 10 to a number and I get such a small number, the power must be negative. So since we raise 10 to a power and we get such a small number, the power has to be negative. So negative what? 1, 2, 3, 4. Negative 4. 10 to negative 4. So then I can come back and write the answer is 2 times 10 to negative 4. How?
Well, when, how come it's not 2 log?
Oh, negative 4. I'm sorry. The answer is negative 4. My apologies. See, I should not try to rush.
Well, what about the 2?
So negative 8. Say it again.
So then would you?
So once I determine this number to be negative 4 and multiply it by 2.
Oh, okay.
Yes, that is 2 times. So 10 to negative 4 is this. So the answer is negative 4. This piece is negative 4. 2 times negative 4 is negative 8. Okay. What about this one? We have not talked about this property. 37. So 10 raised to log 32.
This is another property of the exponential slash log that no other function has. Yes. No, yes, in a way. Yes, the answer is 32. To answer your question, yes. But we're not thinking in those terms. We're not canceling them. You can say that 10 to the x and log base 10 are inverses of each other. So we apply 10 to the power, right, 10 to x, to this number. So since these two functions are inverses of each other, yes, the answer is 32. What I was going to do, now if you're okay with that, I can skip that part, but I wanted to show how we get this. Do we want to see how we get this, or we just want to write 32? Okay, so I don't know what the answer is. So since I don't know what the answer is, I'm looking at this as an exponential equation. 10, some power that I don't even look at, equals y. So I'm going to change this into a log, because it's 10 raised to whatever, log 32 equals y.
And now I want log of something applied to something, base something, whatever, and this something. So remember, this is the base. Don't look at it. This is the power. Don't look at it. And let's see what we get. So what do I have here? It must be 10, right? That's the base, and that's the base. So it must be 10. I shouldn't write it because we normally don't write the base. Okay, what do we raise the base to? This. To get what? Exactly. That's the reason why. Let's compare. Log base 10 of y equals log base 10 of 32. What can y be?
32.
So that's why the answer of 10 raised to log, common log of 32 is 32. And here's the property in general. So 10 raised to log 32 is 32. And here's the property. A raised to log base A of x is indeed. As long as, and this is extremely important, as long as these two are the same. If they are not the same, the answer is not x. Those two bases must be the same. So in other words, e raised to natural log x is perfect. 10 raised to log x is 2 raised to log base 2 of x is, that's it. As long as these quantities are all the same, the two bases are the same. Okay, should we do another? Or we move on? I don't know. I haven't looked at all of them. So let's simplify. 49 on page 497. 2 log 100 raised to negative 3. Again, let's take this one in two steps. We know a property, log base A of b to the x power, that we discussed last time, but you may have not looked at it just yet, so I just want to review it with you. This is x log base A of b, an extremely important property. It will help us solve equations later, exponential equations. So the same thing we're going to do here, we're going to bring the power in front and multiply by 2. This becomes a factor, so negative 3 times 2 will be negative 6 multiplied by log 100. But log 100 can be simplified because the base is 10. 10, imagine now the equation. 10 raised to which power is 100? 2. So then this piece can be replaced by 2. So then the answer is negative 12. You don't have to do the same thing. It's not going to be anything different. Yep, you can. Very good. Okay, let's evaluate. They say let's evaluate any of these using the calculator. We know how to do it. We've done it last time. Let's do one more. Which one would you like from here? They all have either common log or natural log, so they can be done with the calculator in a blink. Which one?
57.
57, log of the square root of 2. Perfect. So 57, log of the square root of 2. And it's important to remember how to verify this. So log the square root. You know parentheses are my best friends. I'm kidding. Okay, so you get the answer and you say, okay, what does this mean? It means that 10 raised to this number is the square root of 2. So let's see how I check that. Power, the previous answer, and it's not going to give me the square root of 2. Let's see if I change it into a fraction, because you can't. You cannot. Should not be able to, because it's an irrational number. So it will not give you the square root of 2, but that's the square root of 2, 1.41. Okay. Let's move on. We looked at the graphs of log, and I would like us to here we are.
Screen's off.
Say it again.
The screen is off.
Of course the screen is off, because I pressed the dock camera. The other class I teach is the dock, and this one is the laptop. They set it up for me through the laptop. Okay. So here we have several questions to practice with, from 7 to 25, they said. For the following exercise, state the domain. We've done one problem, I'd like to do another. For the following exercise, state the domain and the vertical asymptote of the function. For the following exercise, state the domain, vertical asymptote, and behavior of the function. Okay? Let's see what they add up on. Oh, for the next one. For the following exercise, state the domain, range, x and y intercept, and whatever else. So please choose.
20.
Which one?
20.
30 it is.
20.
20 you said?
I can't see it clearly. Is it 20? The last one?
I have no idea.
Yeah, it's 20.
20? This one? Very good. Here they want the domain, vertical asymptote, and end behavior of the function. Great job. Perfect. So let's take a look. 20 on page 513. F of x log base 3 of 15 minus 5x and plus 6. First domain, and then range, and then the end behavior. So I need to find the domain. What do I write to find the domain of a log function? Any log in any base, it doesn't matter. What do I have to write for this function? Anyone, please? Very good. 15 minus 5x has to be greater than 0. Let me refresh your memory, because that was last week and you may have forgotten. So the exponential function is defined on all real numbers and range 0 to infinity. The log function is the inverse function of the exponential. Therefore, its domain must be, that's it. And the range must be, yes, these are carved in stone. That's why I said this function is not a friendly function. It joins the rational and the even roots if you want. So a log, these are not friendly. All these functions, most of the time, have restrictions. They're not defined on all real numbers. So you have to be very careful, and another bell should ring when you see rational, even roots, or log. You should say, oops, well, I have to worry about this function. It's not defined everywhere I wanted it to be. So that's our first step. We solve the inequality, negative 5x greater than negative 15, so x less than 3. So we know the domain is negative infinity 3. Number 2, they want us to find a vertical asymptote. So let me refresh your memory on the graph of a log function with base greater than 1. So base greater than 1, here's the graph. Log base a of x. The pure log function will have x equals 0 as its vertical asymptote. The domain is 0 to infinity. Where do you think will be the vertical asymptote for this function? Exactly. X equals 3 is the vertical asymptote. Very good. And in number 3, they want us to determine the end behavior of this function. Well, I take it that we need to determine what happens here, but I also would like to know what happens here. We know the answer, but I like to do this with a calculator. So in y equals, let's plug in natural log. Oh, it's log base 3. So I don't know if I don't want to use that feature because you may not have that feature in your calculator. So we have to use the change of base formula, which will be log of 15 minus 5x, close the parenthesis, and divide by log of the previous base. So the change of base formula, let me write it down for you one more time. So this function, f of x equals log, yes, of course not, sorry. Thank you so much, sorry about that. So 15 minus 5x can be rewritten, in case you don't have that feature to pick your base, as log 15 minus 5x over log 3. Yes, you can use natural log, but both. Natural log of 15 minus 5x over natural log 3. So that's how I enter the function in the graphing calculator. And now I would like us to illustrate with second and table. And I'm going to put a number as big negative as I can. I don't have to go too far. Let's say negative, that is too far. It doesn't matter really. But it may not be able to calculate. So the answer is, and it's not the whole thing, it's, well, even if it's 14, just 14, it doesn't matter. So it's going to go to positive infinity. So no matter how large negative, right? So negative, maybe it doesn't give me an error if I put as many as I want. Okay. It's a slow growth. So it goes to 22. Okay, so let's see what happens now when we get closer and closer to 3. We know that if I try to plug in 3, what's going to happen? I'm going to get an error. Correct. Very good. So let's say I want 2.9. So yes, I have to be in x 2.9. Okay. So for 2.9, I get negative 0.63. What about now if I want to go very close to 3? 2.999999. Let's go to negative 21. What if I go even closer? Well, we have a cheat sheet here. As you see, here's the graph. You know it's wrong, right? The calculator, please do not copy something like this. The graph doesn't stop here. And there is a vertical asymptote at 3. It will continue towards negative infinity. So this is how I would present the answer. Of course, this is positive infinity, and of course, this is negative infinity. It must be for the same reason that we wrote here. The log is defined only on positive values, and it will return everything. That's what they mean by the end behavior. It has to return everything. And this time, because it has a negative leading coefficient, it will not go from negative to positive, but from positive to negative. A very good pick, Imran. Very good pick. Okay. Questions? to sketch a couple of graphs using of log, and then we look at something more interesting with word problems and equations. It doesn't look at the beginning that these two functions, especially the log and the exponential and log, looks too exciting, but they have tremendous applications, tremendous interesting applications, way more than polynomial and rational. I shouldn't say that. Yes.
I haven't done the +6. That was in the original equation.
In the function, did I copy something else? Oh, I'm sorry, I didn't copy the whole thing. Yes, it was +6. So let me see if anything changes. The domain does not change. The vertical asymptote does not change. +6, it doesn't matter because the domain and range will not change. But thank you. Yes, I'm sorry. I should have not omitted that. It was not intentional. Nothing changes. But the graph will shift up 6 units. But it doesn't matter. The graph will still be the same. Let's go back. Thank you. Nothing changes. The values may change, right? 6 up, everything. So +6. So the values will change, but they are still in the same direction. So the graph just shifts up 6 units, as you see it here. But you know the calculator or my software is lying. We know that. Even if it shifted up 6, it still doesn't matter. It cannot stop here. With the vertical asymptote, it will go all the way to -infinity. Please do not copy something like this on the quiz test final exam, because it's wrong, and we know that. Perfect. Thank you. Sorry about that. I omitted the 6. Okay, I would like us to work on a couple of transformations. For example, 41 on page 514. Let's say log base 2 of x plus 2. This is our f of x. It says sketch the graph, but I would like to sketch it using transformations. Can anyone give us the base function for this?
X plus
Log base 2 of x. Very good. That's the base function. And the only transformation on log base 2 of x is, yes, log base 2 of x plus 2, indeed, left 2. Can anyone give us the domain of this function? But first, let's write the condition. I just don't want to determine the domain without looking at the condition first. The condition is, I have to write
X plus 3 is greater than 0.
excellent, which means this, which means -2 to infinity, which means that the vertical asymptote is, very good, awesome. So let's graph. Is the graph of log base 2 increasing on all its domain or decreasing on all its domain? And how do we know that before we even graph it? Increasing because the base is greater than 1. Thank you. The base is greater than 1. Greater than 1. It must be increasing. So it will always, any pure exponential, any pure log function must cross at 1. Because we know log in any base of 1 is, let's say we forgot. So let's analyze it here. Log base 2 of 1 is 2 raised to which power is 1? That's it. That's why all pure I'm still saying exponential, I don't know why. Pure log functions must pass to the point 1, 0. Now you said you have to shift the 2 to the left, but this function has a vertical asymptote at x equals 0. I must shift the asymptote first. I cannot graph the function before I shift the vertical asymptote. Initially it was at x equals 0, now it has to be at x equals 2 because the whole thing shifts 2 units to the right, to your left. So this point will go 1, 2, and then I shift the entire graph. So here is the graph. of log base 2 of x plus 2. When we shift functions, when we shift left and right functions with vertical asymptotes, we have to shift the vertical asymptote first. When we shift up and down functions with horizontal asymptotes, we have to shift the horizontal asymptote first. Okay, would you like to graph another?
Yes.
Okay, let's look at 46. Age of x equals negative 1/2, negative in front, 1/2 natural log x plus 1 minus 3. Let's identify the base function. Very good. You mean natural log x. Good. Base function is natural log x. First transformation, please, on natural log x. Left 1. So natural log x plus 1, left 1. Second transformation is on number 1. And we have to, yes, we have to put this into 2 pieces, 2 steps. You can put the negative first and then 1/2, or you can put 1/2 and then the negative, but you cannot put negative 1/2 in one step, though. Because there are 2 transformations in there, that's why. Normally we multiply by negative 1/2. We don't multiply by 1/2 and then multiply by negative 1 or vice versa. But these are 2 transformations. So first 1/2. What does this do? Vertical shrinking by a factor of 1/2. And number 3 is a transformation of number 2. And now I put the negative. Yes, very good. Yes, perfect. With respect to the x-axis. And finally, number 4 is a transformation on 3. Yes, perfect. Down 3. Can anyone give us the condition for the domain? What do we have to write and solve in order to find the domain of this function? Greater than, not equal to. So then the domain will be negative 1 to infinity. Can anyone give us the vertical asymptote of this function? Not negative 1, but x equals negative 1. Because negative 1 could be y or x. So we have to say vertical, which is x equal. Okay, so then let's graph it. We start with natural log x. Is it increasing on all its domain or decreasing on all its domain? It's increasing because the base is greater than 1. It must cross at 1. Then you told me to shift the graph left 1, but I have to shift the vertical asymptote first. So that is a negative 1. So now I move this point only one spot. So here it is. So this is natural log of x plus 1. Then you told me to shrink vertically by half, by a factor of 1/2. So here it is. Maybe it's exaggerated a little bit. So this is 1/2 natural log x plus 1. Then you told me to reflect this. Okay, I'm reflecting it. It does not touch the vertical asymptote, please. It goes all the way, but not touching it. So this is negative 1/2 natural log x plus 1. And then you told me to shift everything down 3. So this point goes to 1, 2, 3. Here it is. This is final graph. Any questions before we practice the log properties that we talked about? I'm going to review them first, and then we'll practice. Yes, are you okay? Any questions? Okay, so let me list those three properties before we continue. We're looking at properties of log 6.5. Three properties. We listed them last week, but we didn't get the chance to work on any problems. Properties of log. There are three properties only this function has, no other function. Log of a product, log of a ratio, and log of a power. So log of xy equals log x plus log y. And this goes back and forth. When we are given log of a product, we say expanded into two simple logs. When we are given the sum, we are told condense. Go back and condense into one log. This is expanding, and this is condensing. I'm going to write that. So this way is expanding. This way is condensing. For all three. And we're going to go either way based on the problem we're looking at. So log x over y is log x minus log y. Again, it goes back and forth. And the last one is the power that we just used a few minutes ago. So log base, any base, of b raised to x is x multiplied by log b. Okay, we have different situations to look at. Again, I would like you to choose. I will choose gladly. We should look at condensing. We should look at expanding. We can determine all sorts of values and condense and simplify. So which one would you like to start with?
24.
We want to start with 24. 24, it's asking us to condense. So 24 on page 525. And we have 4 log base 7 of c plus log base 7 of a divided by 3 plus log base 7 of b divided by 3. Right now, this looks completely gibberish. It's extremely simple once we get used to it. So we're going to practice. So what do I see here? Forget about the other two. What do I see here is a number in front of the log. The log is base 7. The log is applied to a quantity c. I know that I'm going to use the third property because this number in front is actually the power of c. So this power 4 will become, this number 4 will become the power of c. Done. The second quantity is inconveniently presented. No problem. I'm going to write 1/3 times that. Same thing here. I'm going to write 1/3 times that. It's the same thing. So then the first one can be rearranged as log base 7 of c to the 4th. The second quantity is 1/3 log base 7 of a, and the last one is 1/3 log base 7 of b. And now it becomes clear what's happening here. What's happening? Like this number 4 was the power of c, this number 1/3 is the power of a. And this number 1/3 is the power of b. But what do we know about power 1/3? What does that mean? Anything with a power 1/3, what does it mean? Perfect. Cube root. Exactly. So then we have log base 7 of c to the 4th plus log base 7 of the cube root of a plus log base 7 of the cube root of b. So now here's a question for you. How come that I couldn't have just the fact that they are all added, just multiply? I can't. So let's go back to the property for a second. The property says I can condense as long as there is one, just one in front. So here I didn't have that. I had a 4 in front, I had a 1/3 in front, I had a 1/3 in front. So I had to clear the numbers in front, the factors in front of each log, which I did. This became power 4, this one has power 1/3, and b has power 1/3. Now I can use this property in which I can have any large number of logs with 1 in front. I will have log of x times y times z times whatever. So that will be the last step. So the final answer will be log of base 7 of c to the 4th times the cube root of ab. But this was not possible before cleaning up each log. So log, and also be careful. All bases must be the same. Otherwise, I can't use the property. But all bases are the same. So this is c to the 4th times the cube root of ab, and that's it. So we condensed those 3 logs, kind of ugly looking, into one log with coefficient 1 applied to this quantity. Very good pick. Any questions on this one before we look at another? Yes, please.
So is there any question that we have in which we don't have the same basis?
I doubt, but if it is, you change the base. Yes, I'll show you an example in a second. Yes, babe?
So because they're both A and B are both under a cube root, we can
Yes.
combine them to one of it, almost like a square root, almost a cube root.
Yes, I have to show you an example like that. Excellent question. Excellent question. So if it happens that we are asked to multiply the 4th root of A by the cube root of B, you will write A to 1/4, B to 1/3. You will find the least common denominator, which is 12, and change both exponents into exponent 12. But now how do I change it? What is 1/4 equal to in terms of blah over 12? And what is 1/3 in terms of something over 12? Correct. So then I will have 3 or 4, and then I will change them into the 12th root of A to the 3rd, B to the 4th. So I can still multiply radicals with different exponents, but I have to find a common. Now, the shortcut would be to multiply by simply just changing the exponents, but I think that this is the best way. Okay, now somebody had a question. I'm sorry, Imran. You had a question on this. So Imran wants to know if I have log base 2 of x plus log base 3 of y, how will I proceed? Okay, here's one way. One way would be to change both into natural log, let's say. Natural log x over natural log 2 plus natural log y over natural log 3. You will not encounter something like this in this course, but who knows? So this becomes 1 over natural log 2 plus 1 over natural log 3 of natural log y. And now these will become the powers. So natural log x raised to 1 over natural log 2 plus natural log y raised to 1 over natural log 3, and now you can multiply them. So then you have natural log x to 1 over natural log 2, y to 1 over natural log 3. I have not seen anything like this in pre-calc, but since you asked, is this clear? You can still add, subtract, whatever, depending on what you're given, by changing the base into one base and then creating that constant as the power. So it's still possible. You're not going to see that. I promise I'm not going to do that to you. There is no point, really.
Okay, so we condensed. Let's also look at some expanding. So let's look at some expanding. We need both. Condensing is extremely useful for equations. You'll see in a minute. So let's